The deepest danger of space is not distance. It is something invisible, something you cannot see, hear, or feel, but it is always there, surrounding every object, passing through metal, passing through skin, passing through bone. Even a few hours outside Earth's protection can begin damaging human DNA at a level science cannot fully reverse. Cells can break, genetic code can scramble, and the damage does not stop immediately when exposure ends. It continues silently inside the body. Most people think space is empty, cold, silent, safe in its emptiness. But deep space is not empty at all. It is filled with high-energy radiation moving at nearly the speed of light. It comes from dying stars, from exploding galaxies, from the sun itself, and from unknown cosmic sources still not fully understood by science. This video is about that hidden reality. It is about why deep space radiation is one of the greatest barriers to human exploration beyond Earth. It is about why current protection systems are not enough. And it is about why traveling far from Earth is not just a question of technology, but a question of survival. By the end of this video, you will understand why radiation in space is not a minor risk. It is a fundamental limit, a boundary written into the laws of physics itself. You will see why shielding humans from it is far more difficult than most people assume, and you will understand why deep space may remain dangerous long after rockets become faster and spacecraft become more advanced. Earth, for all its fragility, is an extraordinary shield. It is surrounded by a powerful magnetic field. This field acts like an invisible barrier, bending and deflecting charged particles coming from space. Without it, life on Earth would be constantly exposed to intense cosmic radiation. The atmosphere adds another layer of protection. It absorbs and scatters high-energy particles before they reach the ground. Together, these two systems form a natural shield that has protected life for billions of years, but this protection is not absolute. It is a thin bubble in a vast and violent universe. Above Earth in low orbit, astronauts still benefit from partial protection. The magnetic field still reaches them. The atmosphere still offers some shielding. This is why space missions near Earth can last for months. Even so, astronauts are still exposed to higher radiation levels than people on the ground. Their bodies slowly accumulate damage over time. But this protection does not extend far. Once a spacecraft leaves low Earth orbit, everything changes. The magnetic shield weakens. The atmospheric protection disappears completely. And the spacecraft enters a region where radiation is no longer filtered. It is direct, raw, constant. This is deep space. In deep space, radiation does not come in small amounts. It comes in powerful bursts and continuous streams. High-energy particles travel through nothingness with almost no obstruction. Some of these particles are so energetic that no known material can fully stop them. They pass through metal walls as if they were almost invisible. This is where the real problem begins. On Earth, radiation exposure is usually limited and controlled. Even in medical settings, doses are carefully measured. But in deep space, there is no limit. Exposure continues every second of every day. It builds up over time. It accumulates in the human body like an invisible weight. And unlike heat or cold, radiation does not give immediate warning signs. A person does not feel it entering the body. There is no pain in the moment. Only later do the effects appear. Sometimes days later, sometimes years later. Astronauts on missions in low Earth orbit already show measurable biological changes, changes in blood cells, changes in vision, changes in DNA repair systems. These effects are still being studied, but they show a clear pattern. The human body is not designed for long exposure to space radiation. Now extend that exposure further toward the moon, toward Mars, toward deep space missions lasting months or years. The risk does not grow linearly. It grows steadily and relentlessly. And beyond Mars, beyond the inner solar system, the environment becomes even more extreme. Galactic cosmic rays dominate. These are not ordinary particles. They are extremely high energy fragments of atoms accelerated by unknown cosmic processes. When they strike the human body, they can cause dense clusters of damage at the cellular level. This is why the question of space travel is not only about rockets or fuel or distance. It is about whether the human body can survive in an environment where the most basic protection we depend on no longer exists. Because beyond Earth's orbit, the shield fails. And what remains is a universe filled with radiation that does not stop, does not slow down, and does not wait. And that is where the real story begins. Deep space radiation is not a single thing. It is a mixture of different forces coming from different places in the universe. Each type behaves differently. Each type carries its own level of danger. And together they create an environment that is extremely hostile to human life. One of the most powerful sources is cosmic rays. These are not rays in the normal sense. They are high energy particles, mostly protons. Some are full atomic nuclei stripped of electrons. They travel through space at nearly the speed of light. Many of them come from outside our solar system. Some may come from distant supernova explosions. Others may come from unknown events in deep space that science has not fully explained yet. These cosmic rays are extremely energetic. When they hit something, they do not simply stop. They break apart atoms. They create chains of secondary particles inside whatever they pass through. A single cosmic ray can trigger a cascade of damage inside human tissue. This is one reason they are so dangerous compared to radiation on Earth. Another major source is the sun itself. The sun is not stable. It releases constant streams of charged particles called solar wind. Most of the time, this is manageable. Earth's magnetic field deflects most of it. But sometimes the sun becomes violent. It produces solar flares and coronal mass ejections. These events send huge bursts of energetic particles into space. When these solar particle events reach a spacecraft, they can increase radiation levels dramatically within minutes. In some cases, the radiation can become strong enough to damage electronics and pose serious health risks to astronauts who are not properly shielded. These events are unpredictable on short timescales, which makes them even more dangerous for long missions. There is also gamma radiation in space. Gamma rays are not particles. They are pure energy. They have no mass and no charge. This makes them extremely penetrating. They can pass through most materials with little resistance. On Earth, the atmosphere absorbs almost all gamma rays from space. But in deep space, there is no atmosphere to provide that protection. Along with gamma rays, there are high-energy atomic nuclei traveling through the universe. These nuclei are much heavier than protons. When they move at near light speed, their impact becomes extremely destructive. They can punch through shielding and leave behind trails of ionization inside materials. Inside the human body, this means direct damage to cells along their path. What makes deep space radiation especially dangerous is not just its strength, it is its energy level. These particles carry far more energy than anything produced in normal Earth environments. Even the most powerful human-made particle accelerators struggle to match them. This high energy is what allows them to penetrate so deeply. Lower energy radiation can often be blocked or absorbed, but high energy cosmic particles do not behave in the same way. They do not stop easily. Instead, they interact with matter in complex ways, creating secondary radiation inside shielding materials. In some cases, shielding can even increase exposure by producing new particles when struck. On Earth, radiation is mostly controlled by natural barriers. The atmosphere filters it. The magnetic field redirects it. Even underground environments provide protection. But in deep space, these barriers disappear completely. There is no filtering layer, no magnetic shield strong enough to block everything. Only direct exposure remains. This is why deep space radiation is fundamentally different. It is not just stronger, it is more unpredictable, more penetrating, and far more difficult to control than anything experienced on Earth. Radiation does not need to burn or cut the body to cause harm. Its damage begins at a level far smaller than human sight. Inside every cell, there is DNA. This DNA is the instruction code that tells the body how to function, grow, and repair itself. Deep space radiation attacks this code directly. When high-energy particles pass through human tissue, they can break the bonds inside DNA strands. Sometimes the damage is small, a single break in one strand. Other times the damage is severe, multiple breaks in both strands at the same time. Cells try to repair this damage, but the process is not perfect. Errors can happen. When those errors remain, mutations are formed. Some mutations are harmless, others are not. Over time, repeated exposure increases the chance that damaged cells begin to grow uncontrollably. This is how cancer risk slowly rises. Not instantly, not dramatically, but steadily as exposure continues for months or years in space. One of the most concerning effects of radiation exposure is its impact on the nervous system. Nerve cells are extremely sensitive. Unlike many other cells in the body, they do not easily regenerate. Damage in this system can affect reaction time, coordination, and cognitive function. Research on astronauts has shown changes in brain activity after space missions. Some experience difficulties with memory and focus. These changes are still being studied, but they suggest that radiation may interfere with how the brain processes information. The concern becomes greater on longer missions where exposure continues without relief. During intense solar particle events, the danger becomes immediate. These events can release a sudden burst of radiation that reaches spacecraft within minutes. If astronauts are outside proper shielding, the body can absorb a large dose in a very short time. This can lead to acute radiation sickness. Symptoms can begin within hours: nausea, fatigue, loss of appetite. In severe cases, damage to bone marrow reduces the body's ability to produce blood cells. This weakens the immune system and slows recovery. On Earth, such conditions require immediate medical treatment. In deep space, treatment options are extremely limited. What makes all of this more dangerous is that there is no single safe threshold for long exposure. Small doses of radiation might seem harmless in isolation. On Earth, people are exposed to background radiation every day. But in space, the same small doses accumulate continuously. There is no escape, no full recovery period. Cells may repair some damage, but not all of it. Over time, unrepaired damage builds up in the body. This is called cumulative exposure. It does not show immediate effects. Instead, it slowly increases risk in the background. The longer the mission, the greater the accumulation. Even the most carefully designed spacecraft cannot eliminate this problem completely. Shielding can reduce exposure, but it cannot remove it. Some radiation still gets through. Some particles are too energetic to fully stop. This creates a silent risk, one that grows with time, one that does not announce itself until much later. Spacecraft shielding looks strong from the outside. Thick metal walls, carefully engineered layers, advanced materials designed to protect human life, but in deep space, appearance is misleading. The protection is not as strong as it seems. Most spacecraft today use aluminum as the main shielding material. It is light, it is strong, it is easy to work with. On Earth, aluminum is effective against many types of radiation, but deep space radiation is different. High-energy particles can pass through aluminum with surprising ease. They do not simply stop at the surface. They continue into the structure and the human environment inside. The problem becomes more complex when shielding gets thicker. It sounds logical to add more material to block more radiation. But in deep space, this can create a hidden effect. When high-energy cosmic rays hit dense materials, they can break apart the atoms inside the shielding itself. This process produces secondary particles. These new particles can sometimes be just as dangerous as the original radiation, and in some cases they spread even further inside the spacecraft. This means that adding more shielding is not always a simple solution. Beyond a certain point, more material does not guarantee more safety. It can change the type of radiation environment inside the spacecraft instead of removing it completely. There is also a serious engineering limitation. Every kilogram sent into space requires enormous energy and cost. If shielding becomes too heavy, the spacecraft becomes impractical to launch. Fuel requirements increase. Structural design becomes more complex. Mission duration and payload capacity both suffer. This creates a difficult balance. A spacecraft needs enough shielding to protect humans, but it cannot be so heavy that it becomes impossible to send into deep space. Engineers are constantly forced to make compromises between protection and practicality. Because of these limitations, scientists have explored other ideas. One of the most promising concepts is magnetic shielding. This approach tries to recreate Earth-like protection by using magnetic fields around a spacecraft. In theory, a strong artificial magnetic field could deflect charged particles before they reach the structure. However, this idea faces major technical barriers. Generating a strong magnetic field in space requires large amounts of power. It also requires heavy equipment that again increases spacecraft mass. Current technology is not advanced enough to create a stable, large-scale magnetic shield that is both efficient and practical for long missions. There are also unknown biological challenges. Even if magnetic shielding reduces some radiation, it may not block all types. Neutral particles and extremely high-energy cosmic rays can still penetrate or bypass magnetic fields. This leaves gaps in protection that are difficult to close. Other advanced materials are being studied. Hydrogen-rich compounds, liquid hydrogen layers, specialized polymers. Each has some ability to reduce radiation exposure, but none can fully stop the highest energy particles found in deep space. This shows a deeper problem. The issue is not just engineering, it is the nature of the radiation itself. Some particles carry so much energy that they challenge the limits of any known material. They interact with matter in ways that are not easily controlled. Current spacecraft design can reduce risk. It can delay damage. It can improve survival for short missions, but it cannot fully eliminate exposure. The protection is partial, and partial protection is not enough for long journeys beyond Earth's orbit. Around Earth, there is an invisible structure that most people never think about. It is called the magnetosphere. It is formed by Earth's magnetic field stretching far into space. It acts like a protective bubble. It deflects charged particles coming from the sun and from deep space. Without it, Earth would be constantly hit by intense radiation. Inside this bubble, life has a shield. Even spacecraft benefit from it when they stay in low Earth orbit. The International Space Station still sits inside this protective region. Radiation levels are higher than on the ground, but still manageable with careful planning and limited exposure time. But this protection has limits. It does not extend far into space. Once a spacecraft leaves this region, it crosses a boundary where the shield becomes weak and eventually disappears. Beyond that point, there is no natural defense left. This is where missions to Mars begin to face serious problems. A trip to Mars is not a short journey. It takes months of continuous travel. During this entire time, astronauts are exposed to deep space radiation without the protection of Earth's magnetic field. Every day adds to the total dose absorbed by the body. This is one of the most overlooked dangers of interplanetary travel. The focus is often on distance and fuel, but radiation exposure is a constant biological timer running in the background. It does not pause. It does not reset. Builds up steadily from the moment the spacecraft leaves Earth orbit. Even a single mission to Mars can push astronauts close to their lifetime radiation limits recommended by safety agencies. This limit is not based on immediate sickness, It is based on long-term risk, especially cancer development decades later. Long-duration missions make the situation even more serious. The longer humans stay in deep space, the more damage accumulates. Cells continue to be hit by high-energy particles. Repair systems in the body become strained. Small errors in DNA replication begin to increase. There is also a psychological layer to this problem. Astronauts cannot see radiation. They cannot feel it, but they know it is passing through them constantly. This creates a silent pressure during long missions, a sense that the body is being slowly affected without any visible sign. Travel time becomes a critical factor. Faster spacecraft could reduce exposure, but current propulsion technology still requires months for interplanetary travel. Even small reductions in travel time do not fully solve the problem. The radiation environment is too persistent. This leads to an important realization in space science. Short missions are currently the only relatively safe option. Trips that last days or weeks can keep exposure within acceptable limits. But missions lasting months or years move into a different category of risk entirely. Beyond Earth's orbit, every additional day increases biological cost. There is no safe zone once the magnetosphere is left behind. Only distance, time, and exposure continue to grow together in the same direction. And that is where the deeper limitation begins to appear. Deep space radiation is not just an engineering challenge. It is a physics problem at its core. This is where the difficulty becomes deeper than metal, materials, or spacecraft design. It is about the nature of energy itself. Cosmic rays carry energy levels that are far beyond anything normally encountered on Earth. Some of these particles are so powerful that they are classified as ultra-high energy cosmic rays. When they strike matter, they do not behave like ordinary radiation. They do not simply stop or slow down. They collide with atomic nuclei and break them apart. This creates showers of secondary particles that spread through everything around them. Blocking this kind of energy is extremely difficult. On Earth, we are protected by the atmosphere, which is thousands of kilometers of air acting as a constant shield. In space, there is nothing like that. Any artificial shield must replicate a protection system that nature has built over billions of years. The problem is that increasing shielding strength quickly leads to another issue. Wait, to stop high energy particles, you need dense and thick materials, but every additional layer adds mass. More mass requires more fuel. More fuel requires larger rockets. Larger rockets increase cost and complexity. At a certain point, the system becomes impractical. This creates a trade-off that has no easy solution. Stronger shielding improves survival chances. But it also makes space travel harder, slower, and more expensive. We are caught between protection and mobility, between safety and feasibility. There is another lesser-known problem. Some materials can actually increase radiation inside the spacecraft under certain conditions. When high-energy particles collide with shielding, they can generate secondary radiation that spreads in different directions. This means the inside of a spacecraft is not just receiving external radiation. It is also dealing with radiation created inside its own walls. Because of this, scientists are forced to think beyond traditional materials. Hydrogen-rich materials are being studied because they can slow down some types of particles more effectively. Water, plastic compounds, and even liquid hydrogen have been considered as shielding layers, but none of these solutions fully solve the problem of the highest energy cosmic rays. Magnetic shielding is another idea. Instead of blocking particles physically, it would deflect them using powerful fields. But to replicate even a fraction of Earth's protection, the energy requirements would be massive. Current technology cannot generate stable magnetic fields strong enough for full spacecraft coverage without extreme power systems. This leads to a deeper question in physics. It may not be enough to engineer better shields. It may require new discoveries in how matter and energy interact at extreme levels. Some scientists suggest that breakthroughs in material science or plasma physics could change what is possible. Others believe new physics may be needed entirely. There is also an uncomfortable possibility that full protection from deep space radiation may not be achievable with current scientific understanding. Not because of lack of effort, not because of lack of intelligence, but because the universe itself sets limits that are not easily overcome. At this point, the problem is no longer about building stronger walls. It is about whether any wall, no matter how advanced, can truly hold back the highest energy particles in the universe. Deep space is not simply distant. It is not just cold or empty. It is an environment that actively works against human biology. Every second outside Earth's protection brings exposure to forces that were never part of human evolution. Radiation is not a rare event in space. It is constant. It is everywhere. It is one of the strongest invisible limits placed on human expansion. What makes this problem so serious is its quiet nature. Radiation does not announce itself. It does not give warning signs in real time. It passes through spacecraft, through materials, and through the human body without resistance that is fully effective. Damage builds slowly, cell by cell, over time, often without immediate awareness of what is happening inside the body. Technology has made incredible progress. Spacecraft are stronger, materials are better, shielding systems are more advanced than ever before. But even with all of this progress, the core problem remains unchanged. Physics sets the boundary. High energy particles from deep space carry levels of energy that cannot be fully controlled or stopped with current methods. The universe does not adjust itself to human limitations. This is why the real challenge of space exploration is not simply reaching new destinations. It is surviving the journey in a way that does not compromise human health in the long term. A short mission can be managed. A carefully planned trip can reduce risk. But long-duration travel beyond Earth's magnetic protection turns into a slow accumulation of exposure that cannot be ignored. There is a deeper realization hidden inside this science. Human ambition is moving faster than human protection. Rockets are advancing. Missions are expanding. Plans for Mars and beyond are growing. But the biological limits of the human body remain the same. The gap between capability and safety is still wide. At some point, this forces a difficult question, not about how far humanity can travel, but about how far it should go under current conditions. Exploration has always been about pushing boundaries, but space introduces a boundary that is not emotional or technological. It is physical. It is built into the structure of the universe itself. The future of space travel may depend on whether that boundary can ever be changed or whether it must simply be accepted. If this story made you think differently about space, consider liking the video and subscribing to the channel. There is much more hidden science behind the universe, and every discovery changes how we understand our place in it.